So the nVidia RTX 2000 series graphics cards have been revealed in a typical 1.5 hour nVidia presentation, and this time I got quite excited and enthused that I decided to make a video trying to explain why the Turing architecture is a significant shift or a paradigm change in computer graphics, and why it's much bigger deal than Pascal or Maxwell or several generations that came before it. Like typically when we have like this line of evolution in computer graphics or nVidia products, you have several iterations of the same way of thinking about graphics. Like when we had the nVidia 5000 series, let's say, because I had this FX 5200 here. Let's say we had the 5000 series, then we had the 6000, 7000. It went several generations. Actually, the cards before the 5000 were, I think, in the same sort of way of thinking. When we had the first programmable shaders, we had pixel shader, vertex shader. We had DirectX shader model 1, shader model 2, shader model 3, but still these were programmable shaders, but the actual architecture of the card was partitioned. Basically there were separate pieces of the chip that ran pixel shader, a different part ran the vertex shaders, and you would say these were fixed function pipelines. Then I think it was in 2006 we had the 8000 series. The first one was 8800 GTX, and I remember the press at the time really ranting and raving about how great the performance is. Shortly after that we had a more affordable 8800 GT, which was a die shrink, or the G92 chip, which was a die shrink of I think it was G90. And yeah, everyone was ranting and raving about general performance in games, but the important part about the 8000 series was that it was essentially another philosophy of graphics. These separate pipelines were unified, and the chip essentially resembled more and more something like a general purpose processor with these compute units. And of course the 8000 series was the first one to introduce CUDA, which is SDK, NVIDIA's SDK for general purpose GPU compute, or GPU. So the 8000 series introduced this unified shader architecture. AMD did the same, and then you had more flexibility in how you're writing the shaders or the code, and the graphics card and the computer graphics had more flexibility, and which meant oftentimes essentially more resources, because not in all scenes you had both of these separate pipelines fully filled up. You had maybe scenes where you could have used entire chip just to do pixel shading, let's say. So the unified shader architecture, and then we had the 9000 series, which was a rebrand of 8000 series, essentially the same chip. And then I think the first GTX name appeared. 200 and 300. I didn't even follow these designations at that time, but there were a whole lot of architectures, and even this same way of thinking extended all the way till the latest, till Kepler, Maxwell and Pascal, and 2018, we could say. This same way of thinking about computer graphics. But now we have something new, fundamentally new, and Turing. And what's new is that, well, a couple of years ago it was quite frustrating to see that nVidia was pushing all this deep learning and data center serious stuff when gamers always wanted just more performance for games, but nVidia was all about deep learning and research and data centers and performance per watt and so on. But actually, when we come to Turing, all this deep learning investment or research actually has led to more possibilities in computer graphics, not just in self-driving cars or pattern recognition or image processing in general, but better graphics, better 3D graphics. So with Turing, what they did, they changed the architecture to be like a system of 3 parts. I will say that the main part is still the same unified shader architecture, which is improved in many ways, of course, over the years compared to 8800, almost unrecognizable, much more flexible, much more powerful, but it's still the, let's say, general purpose compute, although it's not entirely comparable to a CPU, but still it's pretty much general purpose. But in Turing we also make use of this deep learning thing, which is let's say tensor accelerator or neural network accelerator, and a completely new thing which is they call RT core, but yeah, basically ray tracing accelerator. And since they decided to brand this card as not as GTX but as RTX, the RT or the ray tracing part is pretty big deal for them, and actually the CEO, whose name I cannot pronounce, said straight up, this is the world's first ray tracing GPU. And they are doubling down on the ray tracing as the future of graphics. And it shouldn't be a big surprise to anyone that's in the industry. But if you don't know in essence what is ray tracing, maybe you should look it up, because I probably won't give a general explanation, but it's a different way of thinking of graphics, and it's the way that graphics in film, professional offline rendered graphics are done, and it's a much easier way for content creators to do graphics than all kinds of approximations and hacks and methods to approximate how a scene would light up, as opposed to actually simulating light. I think you could say that ray tracing is simulating light. So when you're simulating light, all you have to do is set up a scene and let the hardware and software ensemble, which is called RTX actually, let it do its job and let the dominoes fall as they may, and let the rays traverse the scene and light up areas and reflect and refract as they may. So when we are using ray tracing, we have to simulate the way that light rays propagate through the scene, and it's obviously as there are nearly infinite amount of light rays, or at least let's say billions of light rays that we have to simulate to get accurate representation of a picture. It is of course computationally very intense, especially taking into account that different surfaces may reflect, refract, accumulate light in many ways and multiple times. So it's incredibly computationally intensive, and as they showed in the presentation, I think it was when the first ray tracing algorithm was formulated, that they had the fastest computer was, I think, the Cray supercomputer, and they estimated that you would have to have a Cray supercomputer behind each pixel to drive this algorithm, and that was actually quite primitive compared to what we would expect in AAA games or in photorealism. So computationally, even though we have the computational power has increased hundreds and thousands of times over the years, we still cannot do ray tracing at large resolutions. So what nVidia did with the investment in deep learning and neural networks and this quite clever accelerator chip, or they call them tensor cores, they found a way to approximate part of the scene, well, not the scene, but the output. Let's say we have a matrix of pixels and we calculate every other, and then we just say we know what these pixels are, what color they are, and then maybe we can run or train like an anti-aliasing or filter anti-aliasing neural net that will figure out how to fill in these for free. Well, I think these things are already have been used in image processing and denoising filters and things like that, but I think nVidia with this accelerator now have the ability to run this deep learning super sampling and apply it to video real time. It's precisely because they have a hardware that is capable of doing it. So now that is one way to speed up and to sort of cheat to gain this ability to ray trace at large scale. But still, if you use even this very parallel compute core, we still come short and we still don't have enough speed. So what they also did, they developed an accelerator precisely for calculations that are required to run these ray tracing algorithms, and they call it the RTX core or RT core. So that, in combination with this, enables them to finally run ray tracing at palatable resolutions for actual gaming. And all the while they still have this large complex of, let's say, shader cores that can do traditional rasterization based, like traditional shader based graphics. And then you can combine all of these three, and in the beginning you may say that combination of these two may not be entirely satisfactory to create entirely ray traced games, but we can augment raster graphics with some ray traced elements or reflections, and combine all of these into something that looks like you like you saw or maybe you didn't see in the demos. So essentially they now graphics are no longer just a function of how many shader cores do you have. They are a function of intelligent neural network training and very clever software that can bring all of this together and make it so that the actual developers can make sense of it, and there is a stable, predictable result output video that comes out of this. Now, how do you? I'm sure, as always, there will be a lot of cynicism when it comes to nVidia product launches, and people will be saying, "But come on, they didn't show any benchmarks, and can it run the games that I already have faster, and how much faster, and why would I pay?" By the way, if you didn't know, the 2080 Ti, I think on the website it now lists as $1,200, and even though in the reveal they said $999, and actually we don't know what the demand from the infamous miners will be. So yeah, that might change. But yeah, as usual, there will be a lot of cynicism, and people will be saying, "But it's not that much faster than my 1080 Ti," or that, "Come on, these ray traced graphics are far out in the future. I need to run my current games faster." But these people will not appreciate what this actually means. This means that essentially, and I have to write this down because this is quite painful. Your Pascal is obsolete. Your Pascal card is obsolete. This means that in near future there will be game engines exclusively built around this architecture, and your Pascal card simply will not be able to run them because it will not have the ray tracing performance or the neural net performance. And yeah, so as far as benchmarks, it will be quite difficult to measure the performance in any other way than actual frame rates in games or benchmarks like 3D Mark, because we can no longer talk about shader cores or how many it has, especially if a competitor like AMD comes up with some similar By the way, this is called heterogeneous computing. If AMD come up with their own heterogeneous, I cannot pronounce it, architecture, it will be extremely difficult to compare them in performance other than comparing the actual games, which is actually maybe a good thing. But yeah, benchmarks will be difficult. Also, speaking about price, I think the mining issue or the mining factor will not be an issue anymore, because these parts, the RT core and Tensor core, are useless for mining, or at least for now, or at least as far as I understand, and for the existing algorithms. So the miners probably will not be interested to buy a more expensive chip where half of its die area is taken up by parts that actually do not contribute to running these proof of work algorithms. So this is good news, and I think there were rumors about nVidia introducing a separate card for miners, and that would make sense, because that card would probably have entire area just for compute. So yeah, the benchmarks, the mining. Also, by the way, this deep learning thing, they introduced a couple of more new acronyms. So we already know about RT, ray tracing. We know about, what we didn't know, or what I didn't mention, is DLSS, I think it's deep learning super sampling, and also NGX. Deep learning super sampling is where they something similar to, or exactly what I showed here, but for not just for ray tracing, but for any game, basically. It's a super sampling where they upscale the resolution, but they generate those pixels not just by interpolating between them like we would normally do, but they upscale them with a very clever neural net, which is trained to generate but actually exactly generate new information, to fill these blank spaces with pixels that should be there, that should fit. And they actually, nVidia showed a couple of months ago very compelling demos where they showed a painting program where they could basically erase a lamppost, and the neural net was smart enough to fill the erased area with the building and with windows and the wall that was behind the lamppost. It actually understood how to fill these missing pixels, so they could use this tensor chip accelerator to run this super sampling, or DLSS. There's a list of games, actual games that are coming out very soon that will support this. And the next stage is NGX, or neural graphics, or something like that, where it's even more extreme, where they have like a server farm of, I don't know, gazillion servers training, like encoding visual information in a neural net, and you have your little computer with your little graphics card. And this you receive as part of the game these packages of these neural net topologies, and pre-computed or pre-baked, so to speak, and these neural nets know how to enhance the images based on the what's actually in the scenes of the current scene in the game. I do not fully understand how they are able to do it. I suppose there are like 1,000 different neural nets based on the area where you are in the game, because in the game you will have wildly different scenes with different colors and different structures in them, so you cannot have one neural net trained to be able to enhance all of the scenes in the game, because the scenes are very different. But I suppose they have some advanced structures of these neural nets that will be able to figure out where you are in the game, what should be in the scene, and they are trained specifically to enhance based on your location or something like that. But the idea is that this huge computing power from nVidia's render farm is encoded into these neural nets, which is basically packages of information, and you just receive them along with the game, and they act on the graphics output and enhance it, which is just fantastic idea. So the three-part architecture, all these acronyms, RTX, DLSS, NGX, all this stuff, or let's just call it RTX. This is all nVidia. Now the question is, what happens with AMD? Will they adopt similar hardware heterogeneous computing model? What exactly will they do? Because at the moment they are completely out of the game, entirely out of the game. On top of this RTX software and hardware architecture sits DirectX RT, I think it's called, DirectX ray tracing API, which is standardized, which will be the industry standard, I suppose. So AMD have to create their own hardware, software to interface with this. What will it look like, especially the hardware, is a mystery to me. I think the current Vega architecture may be good enough for the compute, but as far as the neural nets, or especially the ray tracing acceleration and software that nVidia have developed, I'm not sure if AMD have anything similar. So it remains to be seen. And of course we're all interested to see AMD succeed and there be some kind of competition for nVidia, but unfortunately there really wasn't when Pascal was the newest stuff, and now after the Turing it looks very, very bleak for AMD. But well, fingers crossed. They are small, comparatively small, and more agile company. Maybe they can look at what nVidia have done, look at the mistakes or shortcomings of the architecture, and then come in and make something more streamlined or optimized or better, even better. as it often happens in software, like AMD have been doing with Intel. So do not count them out completely, and let's hope they can actually step up to the game and join nVidia in this ray tracing new paradigm of computer graphics. Will I be buying the 2000 series RTX cards? I'm not sure. I'm not really gaming that much. It depends on, for me it depends on whether or not nVidia will offer a mining only chip. If they offer a mining only chip, I will most likely buy the mining only chip, but I am of course interested to have hardware that can run all these latest graphics engines and graphics enhancements on top of the existing engines, because these demos which they showed in presentation were really compelling. This is not an incremental improvement, this is not a gimmick, this is not some kind of just boring new picture filtering or power efficiency enhancement or something like that. This is, I would say, this is as big and as exciting as when shader model 1 and 2 were introduced, where you could literally see very noticeable, like when we went from DirectX 7 to 8 with first programmable shaders, where you could literally see those beautiful reflections and like wet surfaces dynamically reflecting. When you could see that for the first time, it was like a real big step up in computer graphics. And I think what we have now with ray tracing, we are again seeing this kind of fundamental, new, exciting next level of computer graphics. So naturally I will be interested to buy hardware that can run it, whether or not it's the current iteration which they are revealing, the 2000 series, or it's something like a 2000, 3000 or whatever they call them. I think the next gen of this paradigm, within this paradigm, will be far better than this one, because they will have had the chance to learn from experience how to optimize this and improve this, because this is a lot of software on top of a lot of new hardware, and there are many avenues where they can optimize it, where they today don't even really know, they don't have this information on how game developers would like to utilize this architecture. But only when they start to utilize it in mass will nVidia be able to figure out the correct avenues, how to optimize it and improve it. So expect the next generation to be even much faster and more performant than this one. So yeah, that's all I wanted to share. Keep following my channel and you will see whether or not I have a brand new GTX 2080 Ti